Thanks, Joris. Okay, share my screen then. So everybody can see slides.
Yes.
Great. Yeah, as Joris says, I'm Calum, PhD student here that some of you probably know. I'm split between the groups of you from Oog and Jon. And yeah, I'll be talking to you today about some mass loss rates and clumping properties of massive stars. It's probably a bit of a niche title, as I'll be talking a little bit about some other wind properties as well. But this is sort of the main bulk of the project that I'm doing for my PhD. So I'll start off, I guess, by explaining the massive stars bit. So what kind of stars are we looking at for these wind properties? We talk about massive stars as being stars that are above 8 solar masses, and it's sort of, the mass limit is defined by stars that we think have sort of strong enough luminosity to drive radiation winds. So they lose a lot of mass over the main sequence, and then are likely to go supernova and leave behind neutron stars and black holes. So I'm leaving up here some things that we think are sort of important that aren't necessarily massive stars exactly themselves. So obviously we have these winds that are enriching the surrounding medium. And we know that they evolve as these massive stars into other sort of interesting objects like Wolf-Rayet stars and supergiants. And then at the end of their lives, as we say, you'll go supernova and leave behind things like neutron stars and black holes, which we're very interested in now, obviously, with gravitational wave detections. And these are the things that will be forming gravitational wave producing systems. And we can also say that these stars are likely to be proxies for the first generations of stars, which we're going to start seeing with new observatories like JWST and things like that, as the first stars are also thought to be very massive. So we can sort of learn something a little bit about those stars through these stars. So I suppose the first thing to talk about when we're talking about massive stars are the winds themselves in this talk. So you can see that, as we say, massive stars are defined by their mass, and the wind is how they lose mass, right? If that makes sense. So, as you can see, I'm showing a sort of evolutionary diagram here, and this is sort of showing you why the winds are very important, and knowing how much mass is lost is very important, because the evolution is really sort of can be defined by the amount of mass that's being lost. So you can see in the blue track with a high mass loss rate that's coming from simulations that have been done, sort of semi-hydrid consistent simulations of mass leaving a sort of star in a box system. And you can see that this is evolving into a Wolf-Rayet star in its later stages. And if you reduce the mass loss to a third, which isn't that big of a change really on the uncertainties that we have currently, you can see that the end stages of the evolution are completely different. So this is definitely something that's important when you're talking about predicting these kind of exotic events and statistics of massive stars in the later stages. And as we say, the mass loss rates are uncertain, and this is sort of an uncertainty, the reduction of a third that we'll come back to later in the talk, because these theoretical rates that are being used now to, for example, to make these tracks, don't necessarily agree with the mass loss rates that we get from observations, because there's some uncertainty in how we derive mass loss rates observationally. And the reason for that I'll get into now. So we'll talk about what the winds actually are in these stars. So we're not talking about lower mass systems where the winds can be pressure driven or driven by some sort of continuum process in the emission. We're talking about the stars where the radiation itself is driving the mass loss and in line transitions specifically. So we have sort of a schematic here. You can see, imagine a line profile that's moving out away from the solar surface. And as it's doing that, it's being hit by photons. And these photons are interacting at specific wavelengths for electrons that are bound in the atoms. And that's sort of, it's taking in that energy and moving forward. And there's an overall momentum that's going away from the star. And you can sort of see that as the material is being pushed by this sort of momentum radiation pressure, that it's also being redshifted, which means that as it's being, the transition is being pushed to a higher redshift, you can see that now that there's an opportunity for more light to then interact and continue accelerating the material. And it's sort of a runaway process. You can get material that's leaving the star. And it's also something that's inherently quite unstable because, as you say, you have the material being accelerated because of the Doppler shift and further illumination. And then at some point, it might collide with some material in front of it or slow down and collapse back and be hit by something else. And so this is what a wind sort of we expect to look like with this structure. So as you can see, there are these sort of pockets of high density material that we refer to as clumps. And in between the clumps are these regions of sort of tenuous low density material. So this is just a typical simulation of a massive stellar wind that includes obviously the effects of the instability that's done by Florian, who's also in Jon's group. And you can see that if you, well, basically, when you look at a stellar wind in spectroscopy, you have to account for the fact that some of the material is very dense, because as you can imagine, the lines that are being formed in the spectra are dependent on the density. And if we have these overdense regions, it's going to affect the profiles. And if we're diagnosing the material that's leaving the star through these profiles, then we need to know if the density and the emission is being affected. So that's something we have to take into account when we're figuring out mass loss rates from spectra. And there's something that is, well, that's sort of being taken into account a lot of the time now in spectroscopic studies, but they're assuming that most of the material is optically thin. And that's not something that we can necessarily assume, because you can imagine in these dense regions, you have higher opacities. And actually in the tenuous regions, you have lower opacities as well. So you can see this high velocity material that isn't very dense. And so you can end up with some, well, some gaps basically between the clumps where other material or other light can escape. So I'll show you here now a 3D simulation. We're going up in dimensions, and this is one from Nico. And you can see some slices here of sort of clumped material, and you can see that the velocities are very high in yellow and they're very low in blue. And you can see that at certain regions you have these sort of gaps at different velocity spaces where material can escape. So that's going to be important as well, because again, a lot of these lines that we're looking at are being formed at high velocities. And if some of the material is escaping, we're not accounting for that, then that can obviously affect the absorption and emission features that we're seeing. So these are the kind of things that have been a problem in spectroscopic studies. And I'm going to show you one of the sort of main, I guess, the sort of leading problem that causes us to have to think about these structures. And that's that in the UV, you can see some of these line profiles that are being formed. So there's a combination of, well, it's a P Cygni profile, it's a combination of emission and absorption, and all the absorption is in the line of sight here. And it's blue shifted, it's coming towards you and it's being absorbed. And you can see that these are metal line transitions, and essentially with a normal sort of, what would you say, a wind with clumping included in your spectroscopic model, which is being shown here in this sort of light black line, that you're seeing a lot of absorption that you're not seeing in the actual spectrum. So there has to be some reason that the light is not matching this absorption. And the way they were sort of matching this to observations in the past is by reducing the abundance of the metal that you're looking at. But the thinking is that actually these elements shouldn't be processed so much in massive stars, that over the lifetime that you should be seeing these kinds of reductions. So you have to look for other ways to match these absorption features. And one of those ways is by accounting for opacity in the winds. And you can see, as you said, some low opacity regions allow light to escape at high velocities, so we just mentioned. So this is something that's sort of been fairly well established in sort of some test cases from various works. And so now we're getting into the stage where we're able to sort of look at this effect across samples of stars. So how are we going to parameterize these different factors, first of all, to include them in the models and be able to sort of quantify what's going on and get some measurements of these wind structure parameters, and then be able to account for them in the mass loss. And I'm going to show you the three main parameters we look at here, and I'm going to explain them in terms of this 1D simulation now. So we're going back down. This one's from Florian, and these are all essentially the same simulations before, just in different dimensions. And 1D is how we're computing the models that we're comparing to the spectra. So this is the way they're parameterized. You can see that you have this overall mean density in orange. As material is moving away from the star, it's becoming less dense on average, and it's gaining velocity. And you can see these points I've highlighted here are the points that we call clumps. So they're at least twice as dense as the average. And so we then have a sort of a ratio of clumping factor. So how much material is in the clumps, and how much more dense are the clumps than the average material. So we have the density of any clump squared divided by the mean density squared, if that makes sense. So you can think of, if a clumping factor is 10, it means the clumps are 10 times as dense as the average. And we have an interclump density to account for the rest of the medium, which is just, again, the density between the clumps over the average. And finally, we have to think about, as we said, how the clumps are spanning in velocity space, and to account for these gaps in velocity space. So our velocity filling factor is the ratio of the span of clumps in velocity space over a sort of sum of the material that is not being covered. So this one's a little bit more, I think, a little bit hard to sort of conceptualize. And you can essentially think of it as a probability. So a velocity filling factor, as we use it in our models, goes from 0 to 1. And 1 means that a material at any velocity is going to interact with some material. And if it's at 0.5, then it has a 50% chance of interacting as the light's coming out, if that makes sense. So now I can show you the effects of these parameters on the diagnostics. So in the UV, as I said, we have these strong P Cygni profiles. And now I'm showing you what happens if you increase the clumping factor. So how dense are the clumps? And you can see not much is happening in the UV, because this is a profile that's, it's a resonance line profile, so it's dependent on linear density. Whereas if you look in the optical, other mass loss diagnostics, these are a recombination line, H alpha. So that's dependent on density squared. And you can see as you increase the density, you're having a big effect on the amount of emission that you're seeing in H alpha. And so this is sort of one of the ways that we can break the degeneracy between wind structure and mass loss. Because obviously, if you weren't accounting for clumping at all, you would have to increase the mass loss instead to match these peaks. And so there's a degeneracy there, and we are able to sort of break that by including the UV, where there's not as much effect from density itself. And I'm showing you these profiles from sort of a typical O supergiant in the galaxy from the first study that I did during my PhD. And I'm going to show you now the effects of the other parameters. So the velocity filling has its main effect in the UV now, you can see. I'm showing you a profile with 0.5 velocity filling and 0.2. And essentially, as you can see, means that at 0.5, the light has a higher chance of interacting with material as it's leaving the star. And so you have a deeper absorption profile that's matching these lines, or you have a lower amount of absorption. So again, if you reduce the velocity filling, you can reduce the absorption, and that will match some profiles, as we say, if you need to. And finally, you can see the interclump density, which has a similar effect as the velocity filling, where you can see that if you have, again, a higher interclump density, you have more absorption. So that's nice and easy. And now we have all these parameters. How are we going to determine any of them? So you can see there's a lot of degeneracy, and it's not only with mass loss, it's also with some other parameters. So you have things like abundances, temperatures that you have to account for. And we want to be able to do this, as we said, for samples of stars. So the way we're doing this is by optimizing models with a large number of parameters. And these models are fast wind models, which are sort of one-dimensional, spherically symmetric stellar models that include the star and a wind, and then produce synthetic spectra. So we can change all these parameters and they will affect the emergent synthetic spectra differently. And to be able to create a model that fits our star best, we're essentially varying all of these parameters and trying to find sort of the best solution combination of all the parameters. And the way we do that is by using an algorithm that we call a genetic algorithm, and it works by the same principles as genetic evolution. So the idea is that you have, showing sort of a schematic here, you have an initial population of models in these red dots that are kind of random throughout your parameter space. And as time goes on, so from the initial population, you rank which models fit the best just by chi-square. And then you can mix and match parameters from the best fitting models and create another population. And you can see this is sort of what's happening here, where more models are being confined to what you think is their best fitting region. And so you sort of iterate over time with meshing different parameters from best fitting models. But you also want to make sure that you're not getting stuck in sort of local parameter solutions and local minima in your parameter space. So you also introduce mutations, and that's the same thing that is done in evolution. So you're just throwing in random numbers at the parameters after they're being refined to sort of increase the exploration of the parameter space. So this is sort of a very efficient way of searching for a solution in a large parameter space, and we sort of just iterate the populations until we reach some kind of convergence, and that's how we find our best fit model. So that's what we're going to do. We're going to apply this algorithm with fast wind to a sample of stars, and the first sample we look at here is a sample of well-studied O supergiants in the galaxy. So we're taking a sample from a previous study that looked at these stars, also with clumping, but not with the effects of the opacity parameters that I was discussing before. And I'm just showing you here these 8 stars as O supergiants in the range of, you can see, sort of, it's a fairly narrow range of masses and temperatures in the context of O stars. But these are the stars with the strongest winds. It's a good place to start. So I can now show you an example fit. So this is the best fit for one of these stars. And you can see that on the left here, I'm showing a subset of the line profiles. This isn't everything that we're fitting, just some of the important diagnostics. And we're mainly focusing on wind diagnostics, and including some others as well for abundances and things like that, and just for temperatures as well. So all sorts of stuff. And you can see the fit quality is quite good, which we're happy with. And the red line here is the best fit. And the green lines are models that we find to be statistically indistinguishable to the best fit. So we have a family of solutions essentially that we say are all statistically indistinguishable. And you can see those here highlighted in our model distributions in this sort of red best fit region. So each blue point here is a model, and I'm showing you distributions for different parameters. So you can see we're fitting things like temperature, surface gravity, mass loss, etc., etc. And essentially what this is showing is that we have the ability to pick out a good model, essentially. So there is a sort of minimum in the chi-square that we can say this is our best fitting model, and it's pretty well defined, more so for some parameters than others. And you can see that the mass loss is actually pretty good. And then if you notice, we have some red points that are over the top of the blue points, and that's just us trying to define some errors at the end. So these are extra models we run after the genetic algorithm that are just varying one parameter at a time, sort of orthogonally, to see how that affects the statistics of the fit. So yeah, we're able to fit all these profiles simultaneously using lots of models, and this comes out automatically, and we have our best fit. And I can now show you if we have a similar sort of set like this for each of the 8 stars. We can then come out with some averages. And I'm again showing you just some examples for one star. And here you're seeing that for each of these new parameters that we're introducing, the clumping factor, velocity filling, and intercom density, we're getting solutions but for some of them it's a little bit harder. So you can see the clumping factor is well defined. The velocity filling is fairly good. You can tell that it's definitely intermediate and not very high or very low. For the intercom density, it's a little bit harder because, as we say, it's a similar effect as velocity filling, but a little bit less pronounced. And so it's harder to sort of pick out. But anyway, we're able to get some information. And here you can see we have average clumping factors of about 25, anywhere between 20 to 30 really. So again, 20 to 30 times density of the average density in the clumps. Velocity filling is, again, sort of about half of the velocity space is covered by clumps, maybe just under half, going down to a third. And you can see that the interclump medium is about 0.1 of the density of the average. So this is all well and good, and I can show you these sort of compared to the mass loss as well, which is very good. It's very well defined, which we're happy about. So we're able to sort of break down the degeneracy between, or not break, just break the degeneracy between clumping factor and mass loss rate, and get well-defined values that we can then use to determine how the star evolves, which is nice. So finally, this is the mass loss rate for the whole sample. So I'm showing you these 8 stars, mass loss rate against luminosity. And you can see in blue here is our sample, our spectroscopic mass loss rates for our sample. And then I'm overplotting theoretical predictions. So using best fit parameters also from our fits, we can then predict mass loss rates. So using things like the temperature, the luminosity, we can predict mass loss rates with some theoretical recipes. And you can see that the mass loss rates here from Vink, which are the ones that are typically used in stellar evolution models, are a little bit high compared to the ones we're finding from the spectral modeling. So again, they're about 3 times lower, which, as we showed at the beginning, can be a significant change in the evolution of a star. And some recently some new rates have been computed by Robin, who was a PhD student here, who finished last year, and some of his results are matching a little bit better, which is quite nice. So we can sort of say that we're improving the theory a little bit, and we're able to predict hopefully more accurate mass loss rates and get better estimates of stellar evolution. So this is sort of summary of the first study of these galactic O supergiants. And now that we have, I guess, our estimate, our sort of proof of concept, I would say, we say that the method we have works. Now we want to see how these sort of the mass loss rates and the clumping factors are being, I say, how are they affected by fundamental stellar parameters? So, for example, metallicity. And one of the things that we think is that because the mass loss is being driven by these sort of line transitions that are generally being metal line transitions, that if you decrease the metallicity of the star, there are less of these transitions in the wind, and so the overall mass is lost is decreasing. And again, this is a prediction from Robin, and there are a couple of other predictions out there as well, but they're all kind of agreeing in saying that the mass loss should be reduced a little bit as the metallicity is decreased. So this is a plot just showing a couple of different metallicity environments. So the galaxy we say has solar metallicity, the LMC, the Large Magellanic Cloud has about half of that metallicity, and so the mass loss rate is reduced, and the Small Magellanic Cloud is even lower, so it's 1/5, and again the mass loss is reduced. So we want to be able to test the mass loss in these different environments, and then also see if the mass loss are being reduced, how are the factors that are relating to wind structure being affected? So things like clumping should probably also be affected by this sort of reduction in wind strength. So this is what I'm working on now. So we have a new sample of stars in the LMC and the SMC. So we have 20 stars in the LMC, and we also have a pretty good range in stellar parameters. So you can see plotted against some evolutionary diagrams of different masses, we have a much larger spread. in orange than our galactic sample, which is shown in blue, which really just only occupies this sort of upper region. And then we also have a similar coverage in the SMC, but slightly less, so only half the sample size. And these are brand new observations that are coming from the Hubble Space Telescope, from a proposal from Laurent, who some of you may know, who was also at Leuven recently, now in Brussels. And we're using optical spectra for our LMC sample that come from a previous study in the optical, that was the Flames Tarantula survey on the VLT. So we have high resolution, high signal to noise spectra in the optical and in the UV. And as we've seen, we're able to diagnose some wind parameters from that in the galaxy. So we can do the same in the LMC. And I'm going to show you our sort of first results. So this is a bit of a sanity check plot where I'm showing you the circles are all of the stars in our LMC sample plotted against effective temperature and surface gravity. And I'm splitting the sample into luminosity class. So we have supergiants in blue, regular giants in orange, and green are dwarf stars. And the crosses are previous studies. So we want to compare what we're finding to previous studies, just to make sure that nothing crazy is coming out. And we're finding that in previous studies here for giants and supergiants from Ramirez Agudelo, which is a method, which is a study that uses a genetic algorithm, but only on optical spectra. So they don't have the same range of diagnostics as us. They don't have the UV. And we can see that in general, these blue points and orange points are kind of agreeing, and there's a little bit of scatter, but it's not systematic. And that's quite nice. So we can obviously say, hopefully we're improving on the results when there's nothing systematic here, and maybe some stars, there are some issues that we need to deal with, but nothing dramatic. And then there are some other previous studies on the O dwarfs, and this is from Sabin Sanhulian in 2017 as well. But they're using only grid fitting, and they don't have a genetic algorithm, and also only on the optical. And you can see here in the green points, maybe there are some systematics coming in differences between previous studies and our studies. So hopefully we're getting good stellar parameters out from our fits in the GA. So I can move on from this and show you some example fits. So here's an example of a hot star. This is a dwarf star, and sorry, the temperature axis is hard to read, but this is somewhere around 45,000 Kelvin is our temperature. And again, we're able to obtain pretty high quality fits, I'd say, sort of again on the same order of quality as we did in the galaxy, which is very reassuring. And we have, again, well-peaked distributions for a lot of parameters, and the mass loss as well. And you can see now that it's becoming a bit harder actually to define some of these wind properties. The distributions look fairly flat, but there's still some sort of statistical significance here. And this becomes sort of clearly apparent when we look at stars of lower temperature. So now that we have this range in stellar parameters, we can start to see maybe some trends with parameters emerging. And again, the fits are okay. We may be having some difficulties in the UV now that we're getting to lower temperatures. This is something around maybe 35,000 Kelvin, so 10,000 Kelvin lower temperature. But now you can see that, well, there is some statistical evidence that the wind parameters are changing, right? So this is definitely a different solution than we were finding before for some of the other stars. So now we can look briefly at the trends of these parameters, or the trends of these wind parameters with, I'm just showing temperature here, because you can kind of see maybe some of a trend emerging. Of course, there's a lot of scatter here, there's large uncertainties. And especially at low temperature for some of these parameters, there is essentially no constraint. So you can see here that the error bar is essentially our entire parameter space for velocity fitting for one star. But overall, you can kind of see some maybe general increase in temperature from general increase in these parameters with temperature. Essentially that we have very low values, especially for the velocity filling and the interclump medium filling. And these are increasing at high temperatures, but maybe not, we're not able to identify exactly how, but it does seem like there's some evidence for higher values at higher temperatures. And maybe this is also in the clumping factor as well, but it's less pronounced. And maybe I can mention briefly here that there are some other studies that are doing similar things that we're doing, and actually on larger samples in the LMC, but with lower quality spectra. So it's a little bit, they have much larger uncertainties on these values, but they're kind of finding similar trends. And these are studies that are being done with from some of our collaborators in Amsterdam. Maybe some of you know, so Sarah Brands and Frank Pax is also moving into doing some of this as well. So now that we have some idea of, again, the clumping factors that we're determining here, we can see what effects we have in mass loss. And for now, we're just going to look at the right-hand side of this diagram. So it's the same as I was showing you earlier, just luminosity and mass loss rate, but now for our LMC sample. And if we look at the right-hand side, where I've drawn this line here, we're now, well, I'm not color coding the lines anymore because I'm showing you the difference between the luminosity classes instead. But here I'm showing that we have a fairly, there's kind of a trend in mass loss here. And the black line is our fit to the whole sample. And the dotted line at the top is the pink mass loss rates that we were predicting against before. And the dashed line here is the mass loss rates from Robin. And you can see that, again, there's a reduction between what we're finding spectroscopically with the theoretical predictions from Vink that are used in stellar evolution calculations. And this is a factor of maybe 6 times lower, as opposed to before it was 3 times lower. So maybe there's even a bigger effect at lower mass helicity. And again, some better agreement with the rates from Robin, but not perfect, which is, I guess, to be expected. But now we also have a problem on the left-hand side of the diagram at lower luminosities, and that is that some of these stars have weak winds. So the mass loss rates are much lower than predicted in basically any case. So it's much, much lower than the Vink rates and much lower than Robin's rates as well. And you can see that this is kind of why I've split this diagram in half, and that there's something else going on here. It's not our typical wind physics. But it doesn't seem to be the case for all the stars, which is interesting as well. So there are some explanations for this. The theory is sort of still being worked on, but one of the prevailing ideas that's been suggested for a while and recently tested again by work from people from Jon's group. So this is from Sis Legay, who was a master's student in the group and has now moved on to do his PhD. And this is a simulation of showing the difference between an O supergiant, as you can see, corresponding luminosity class in the other diagram, compared to an O dwarf. And the thinking is this is the clumping was essentially just the wind, but you can see some clumping effects through the temperature. So this is just a temperature gradient. We have high temperature regions being highlighted here compared to low temperature regions. And you can see that generally the O supergiant wind is lower temperature. And the idea is that there's a lower wind density in the dwarf star. And so there's a lot of shock heating, as you can imagine, as we said, a lot of material colliding in the winds, generating shocks and increasing the temperature. But at low densities, it's harder to cool down. So you end up with more ionization throughout the wind. And so you have less, less material that is in the ionization stages of the lines that we're looking at. So the line strengths are being reduced. And so the mass loss rates we're seeing from the lines that we're diagnosing through spectroscopy are going to be lower as well, because the lines are lower and we're not accounting for these temperature deviations, I guess, between the different types of stars. So maybe that's one solution that we can start looking into. But we can just, again, have an overview for now. This is sort of like the point we're at. And now we're starting to look into, looking into solutions to some of these problems. So in summary, as we said, maybe about 6 times lower spectroscopic mass loss rates is predicted from previous theory, and some of the newer theory is a little bit more in agreement, you can say. And now we have looking at our average wind structure clumping factors. So you can see the average clumping factor throughout the full sample is about 15, which is a little bit lower than what we're finding in the galaxy. But you might think, well, what about all these stars that are throwing the measurements off? Sorry, I should say that the whole sample is about 13. And if you take out these measurements on the low end, then it goes to about 15. And if you only look at the low end, you can take it down to something like 10 or 8 even. And sort of similar numbers, I'm showing numbers derived in a similar way for the other parameters. So looking at the full sample together, the clump filling in velocity space is about a third. I mean, if you only look at these stars, it can go a little bit higher. So sort of almost in agreement with so what we're finding in the galaxy, excuse me. And then again, sort of similar densities of the material in between the clumps as we were finding in the galaxy as well, maybe a little bit lower. I'll not move on just yet. So that's sort of like our final results for now for the LMC sample. It's kind of something we're still working on, and hopefully over the course of the rest of my PhD, we'll be able to more concretely define some of these parameters and look for trends, and again be more concrete trends, maybe with stellar parameters and also with metallicity for these stars, for these parameters over the sample. And obviously the next thing to show you would be the SMC sample at lower metallicity. This is something we haven't done yet, and it's something that I'm starting to work on now that we have these results. And the reason that it's not been done yet is because we have postponed it a little bit because we had an opportunity with some shiny new data that came out. So this is sort of, I say, a little bit of a detour from the story that I was lining out at the beginning of the talk. So now we have new data that's coming from the Hubble Space Telescope again. It's called the Ulysses Survey. So this is a legacy survey to build a library of observations of massive stars in the UV with a lot of Hubble time. And this is designed to get observations of 250 OMB type stars, massive stars in the LMC and the SMC, again, over a span of different spectral types and luminosity classes. And you can see that this is pretty exciting for us. So you're getting similar diagnostics as what we've been working on to find mass loss rates and wind properties in our samples, but now the sample is 10 times larger. And we can't do exactly what we've been doing yet because we don't have the optical data, but that's also been taken. So there's a follow-up survey that's planned to complement the UV survey, and that's all the observations have almost been taken now with X-Shooter on the VLT, which covers the optical range and also the near infrared. And those are going to be coming out soon. But in the meantime, we thought we have all these stars. What can we find in terms of wind properties just from the UV? And I guess, well, I've skipped ahead a little bit, but now that we have all these stars, well, we need to know a little bit of something about these stars before we go rushing into wind parameters and doing comparisons with the stellar parameters. So we have sort of very sort of quick estimations of stellar parameters for this whole sample from some literature studies, and most of them are from spectral type calibrations. So maybe these temperatures and luminosities aren't perfect, but they're pretty, they're sort of fine for what we want to be doing for now. And I'm showing you the sample in these sort of blue points, again with just some evolutionary diagrams shown over. And I'm showing you the sample that I'm looking at in my PhD in orange. So you can see that there's a big increase in sample size and coverage here, which is going to be super exciting for, again, looking at these kinds of wind properties. And so we can use the luminosities and temperatures from these calibrations to get some other stellar parameters, so we can compare them to these evolutionary tracks and really just mix and match the points, what tracks are they closest to, And from there, we can find some other parameters, things like radius and masses. And that's being done using the tool Bonsai, which is a Bayesian tool that finds, I guess, the best matching evolutionary diagram or evolutionary model for your star. So now we have a couple of stellar parameters to work with, without having to do all the different atmospheric modeling we would usually have to do. Have some basic estimations. So now we have, well, as I said, what wind parameters can we determine to compare against these parameters and try and figure out what's going on in the winds of these stars from just the UV. And one thing we can look at are wind speeds. So I've been highlighting all these different uncertainties in mass loss rates, et cetera, but there's another sort of uncertainty if you think about not necessarily stellar evolution itself, but the mass mass loss being ejected into the ISM and the effect of that on interstellar regions. And you can think of that as energy input, so mass is being put out into the surrounding medium, and we have a mass loss rate that's included here, and also a speed. So one thing we want to figure out is what are the speeds of these stars, because there are some mass loss rate predictions, and we've seen we can kind of scale these to match observations if we want to, but there aren't so many predictions for wind speeds. And so that's a component we need to figure out. And as I was showing before, sort of this is something we can find just from the UV, because as you can see, the wind speed is increasing as you get further away from the star. The wind's being accelerated by these line transitions, as we discussed already. And far away from the star, it's no longer being accelerated and it's at a maximum speed. And we can determine what this maximum speed is just from the UV, because we have these P Cygni profiles that we were looking at before. We have this massive absorption component, which is blocking light in your line of sight. And it's blocking so much light that actually no light is getting to you. And so you know that when you start seeing light again, there's no material at that high speed coming towards you. So you can say that that's the maximum speed of the wind material. And you can measure that essentially directly. So here in blue, I'm showing you a little zoom in of just measuring, again, the zero flux, maximum wavelength, maximum velocity. And we can also model this with sort of simplified stellar models. So now we're just doing a very quick P Cygni profile simulation and matching that up with our direct measurement, or sort of comparing that to our direct measurement, matching it to the line profile. And this is was something we're able to do very quickly. And yeah, we're just seeing the wind of the star, or sorry, the wind of the speed of the wind is what I meant to say. And then we can compare this to what we're determining from the models. And generally these values agree, which is nice. So we can use these simplified models to determine wind speeds, and they also agree very well with those who we're measuring directly just from the zero flux. And so the maximum speed of material we're seeing. And you might think this is a really nice and easy thing to do. You can just measure it directly and the models agree. But obviously it's not the case for all of the stars. We have 250 stars and not all of them have these nice line profiles. And so we sort of split these into a couple of different categories. And we're looking mainly, the results I'm going to show you are for stars that have these really nice saturated wind profiles. And there are some other, the majority of the sample are not like this. So you have some stars that are have strong wind profiles, but they're not saturated. And some of them, as you go further away from having strong winds, you have essentially less diagnostics in these lines, less strong wind lines. And so you can't really find wind speeds. So we're looking at these stars basically with strong wind profiles. And let's see how they trend with temperature. So I'm showing you now just our points for, well, our measurements of wind speed for the LMC and the SMC in blue and in red respectively. And all the circles are the points that we're able to measure from the Ulysses sample. And you can see that there's a fairly nice trend of increasing wind speed with temperature. But in the SMC, we don't have as good coverage in temperature space, so we're adding some literature points from previous studies. There have also been some other studies that have looked at terminal wind speeds in the SMC and the LMC. So these are the smaller points you can see on the diagram that are being included in this fit just to increase our coverage. And you can see here the best fit to, for example, the LMC with an uncertainty, and you can see, so this is a fit. The dark line is just a fit to the stars that we've measured, and the dashed line is including the literature. You can see there's actually not much of a difference here. So we're fairly confident we can include the literature for the SMC and not throw off the values. All the literature measurements are taken using similar methods as well. So we're fairly confident that these are nice and sort of fine to include. And you can see that the gradients match very well, which is good if you're sort of expecting there to be just a general decrease in wind speed with metal-Lisi, because as we said, the lines are the sort of the wind is being driven by these metal line transitions. Reduce metal-Lisi, reduce wind speed, reduce things like mass loss, wind strength, etc. So this is a fairly nice finding. And this is a very nice trend, essentially. The uncertainty isn't too large. So you can see a scatter here of 200 kilometers per second in the LMC, about 300 for the SMC. And that's a pretty, I would say, a good, well, if you wanted to predict, for example, a wind speed using a temperature and the uncertainty is only 200 kilometers per second, that's pretty good. And so we're sort of finding evidence that temperature is a good way to predict terminal wind speed when you don't have access to the UV, as most of the studies that have been done in the past didn't really have access to these large scale UV surveys. And previously, they've been using escape speeds to predict the wind speeds, and you can see the sort of a logical thing to do, because once material is able to escape from a star, it probably scales with the wind speed as well, in the same way that once anything, if a space shuttle leaves the Earth, it gets out of the escape speed, then the speed can sort of trend with that. So this is what's being used to predict terminal wind speeds up until now, and we can see there's a bit of a larger scatter, essentially because escape speeds are hard to determine, because we need, as you say, the evolutionary models to match up, and this is not the easiest thing in the world to do. It's before we just had temperatures and luminosities, and you're taking those to match with points on evolutionary diagrams to get radius and masses out. There's a bit of uncertainty there. So maybe the temperature is a better way to go for predicting wind speeds. And you can see here I haven't included the literature points, again, because in the literature, not a lot of escape speeds are being determined, and not in the same way that we would be finding them necessarily, not with the same models. So they're not super consistent, so they're not included just yet, but maybe we can do it in the future. So we wanted to see how much of the scatter on each of these diagrams is coming from inherent variability in the stars. So we did a very quick sort of set of simulations. As you can see, line profile simulations, kind of similar to what we were doing before, but in a more sophisticated way. And so you can see now these are time dependent, and I'm just showing you, well, the black line is initial conditions basically, and then it's evolving with time. And you can see that with time, the profile is changing, and the maximum velocity we will be determining from the profile is changing as well. So this is simulations that have been made to be similar to the observations we have, so signal to noise of around 20, and time coverage that would be similar to clumps moving out from the wind, causing variability. And you can see a scatter here just directly from measuring this, are on the order of 5%. So that sort of accounts for some of the scatter, which is nice as well. And now we're going on to take these measurements to see if there's a metal-Lisi dependence. So as we've shown a little bit of the LMC and the SMC before, can we compare to the galaxy as well, where large surveys have been done in the UV on terminal wind speeds? And you can see that there's a little bit of a difference between the two slopes, but in general, you can see wind speed decreasing with metal-Lisi, which is quite nice. And you can determine sort of a wind speed metal-Lisi dependence here that agrees with predictions from some models in the past as well. So that's quite nice. And so this is sort of our little summary of the terminal wind speed study we've been doing. And we can see a strong trend of terminal wind speed with escape speed, as is predicted. But maybe the trend is a little bit more robust with temperature. And there's a scatter of maybe 10 to 20%, and some of that is inherent variability to the star, and some of it is just differences in different stars. So there's not, you wouldn't expect exactly 2 stars at the same temperature because of other parameters to have the same wind speed. And I'll just mention, we have wind speed with Ulysses. So that's kind of everything I've done so far for my PhD. And I can give you a summary. As we said, we've studied wind speed or wind parameters in the galaxy on some supergiants, and we find mass loss rates that are a little bit lower than previous predictions used in cell revolution calculations, and agree well with newer predictions. And we're able to find some factors that describe the wind structure and the clumps in the wind for both of these samples. We're able to constrain them fairly well in these models, as we've shown before. And maybe there's some preliminary reduction in average values with Ulysses as well as we move to the LMC. And finally, we're able to also see some Ulysses dependence of terminal wind speed from wind speeds that we're finding in the UV using the Ulysses sample. And I could put up future work, but I'll just say future work. And that's moving on to the SMC sample to be able to sort of fill in these 2 boxes copied over to the SMC and get to a sort of nice trend of different wind factors, mass loss rates, clumping factors with Ulysses over different cell parameters. And I suppose I can leave that there. Thank you all for listening, and I'm happy to take any questions you might have.
Thank you, Calum, for this nice talk. So now there is the opportunity for questions. If you have a question, please say so in the chat, and I will call out your name. I'll see that, not surprisingly, Florian has some question or comments.
Yeah, I have several questions, but first of all, this is really nice. I mean, it was like, I felt like in a candy store, so many nice results. Now, coincidentally, I gave this morning a talk in Amsterdam about wind clumping versus metallicity. So I will start my questions with that. So if you go to the GA run of your LMC, so I don't know which slide this was anymore. I was somewhat confused that, so your H alpha line is quite well fitted, it seems. So you have a good constraint on the mass loss rate, but then there's a huge dependency on the clumping. And why is this exactly? Since, I mean, in the H alpha, you're measuring mass loss rate and the clumping together, right? So if one is well constrained, how can the other one be so huge in variation?
Yeah, so I suppose the nice thing about the mass loss rate is that you have diagnostics in both, as you say, H alpha and also in the UV. So you can kind of get some limit on just by the degeneracy there, or the degeneracy there being broken by introducing this clumping factor, right? So you end up with a limit essentially, as you can kind of see here, where we have a bit of an upper limit that drops up really fast, and then it's not quite as well defined as we had in the galaxy. Before it was like this super small peak, and now it's a little bit of a gradual decrease. And the clumping factor, I think, is just the fact that we only have these optical diagnostics, and we're also missing a lot of information here. You can see we're cutting out the middle of the lines because of nebular contamination. So I think it's just a little bit harder to find to constrain these clumping factors.
So this is for one star, I see.
Yeah, exactly.
Or is this for all stars used in the sample?
I mean, it's a little bit, you can sort of see here, the uncertainties are fairly large in general, right, across the whole sample, which isn't, ideal, but it's sort of what we have currently. And at least it's a little bit better at high temperatures where we have these clear diagnostics as opposed to these lower temperatures where we have higher uncertainties.
Yeah. So, in analogy with your, this was one question I had, but you answered already for me. So you have this derived from your SCI fitting the terminal wind velocity dependence on metallicity, which
Yeah.
agrees quite well with an older work by Klaus Leitler. So I was actually wondering now, have you done something similar, or are you planning to do something similar as clumping versus metallicity, a power law relation? Because that would be something I'm extremely interested in.
Yeah, I definitely think it's something we're going to try to do in the future. I suppose now we're just not doing it because we only have 2 points, right? The Galaxy and the LMC. But for sure, we'll see what we can get out
So
once we
what's up with the, so
SMC
is
is.
there SMC data somewhere lying around, or what's the idea?
Yeah, exactly. So if I have, where was the slide? Our sample, our full sample in the UV plus the optical from Laurent's proposal, and you can see that we have these SMC stars in green. So we have a sample that we'll be able to study. 10 stars we can do on a fairly quick time scale. I mean, it's not going to be next week, but it's going to be within the course of the rest of my PhD. And then obviously we can try and get something out, and it's not going to be as nice as, you know, the terminal wind speeds where we have 200 plus stars. But hopefully we can get something out. And then obviously in the not too distant future, we're able to do a similar thing for 200 stars, and then hopefully we'll be able to get some really robust ideas of what's going on with metallicity.
Okay, cool. Thanks.
Thanks, Florian.
Thank you. Has anyone else has a question? The talk was very extensive and well explained, so there might not be. Yes, Karan, please.
Hi, can you hear me?
Yeah.
Hi, Calum. Thanks for the nice talk. I had a quick question. So because you do all of this analysis in one dimension and in 1D, would there be a benefit of extending to 2D and 3D? Because even in our own groups, we are soon getting an extension to 2-dimensional and 3-dimensional models, hydrodynamical models. So would there be a benefit of doing the same kind of analysis in a higher dimensional scheme?
Yeah, definitely. I mean, it's just more computationally expensive is the reason that we don't do it now, right? So you can definitely imagine that, as you say, going back to these simulations, you know, if you're trying to determine a clumping factor or sort of any kind of wind dependence, wind structure dependence or mass loss, et cetera, in 2 dimensions, you have so much more information than just looking at this 1D slice. So I think we'll be able to learn a whole lot if we're able to do this in 2D. We'll have a lot more information coming out for sure.
If I can just have a quick follow-up on that. So if you were to indeed do it in 2D or even 3D, would just a clumping factor be enough, or would you need to introduce something else?
Yeah, it's a good question. I think there would be an opportunity to introduce something else, but I'm certainly not an expert in that, so I don't know exactly how to, you know, quantify what it would be. But I do think being able to look at, you know, for example, the how this is affecting the winds in 2 dimensions. So, for example, the extra effects of light leakage, or, you know, as clumps are being affected by, as you can see, they're sort of the clumps aren't consistent at the base of the wind as they are further out in the wind, and so that's going to be affecting different regions differently, and different lines are formed in different regions, for example. So even now, the clumping factor, I suppose it's something I skipped over, isn't completely constant throughout the wind. It increase. Oh no, sorry, that's not true. It is constant. So maybe it would be good to introduce, distance, radial distance dependence, and things like that as well. 2D.
All right. Thanks, Calum.
Cheers.
Okay, then I think we have one last question from Pablo.
Yeah.
Hey, Calum, can you hear me?
You are very. I don't hear you well.
Yeah.
One quick second. Can you hear me better now?
Yes,
Yeah.
excellent.
Yeah.
Okay. So I'm just curious, can you apply all this to WNL stars? I mean, when you push towards stars near the Eddington limit, or is there some caveat to just applying all you've done to observations of those?
Yeah, so I think this is something that is being worked on. So stars that, as you say, are kind of on the limit of like our typical O star region and it going into the WR stage. There are some sort of modeling tips and tricks I think that you can do to be able to sort of carry these models over a little bit. But I'm not sort of an expert to explain to you, I guess, the caveats that are coming into the models here and what really are the differences between the two samples, the two types of stars. So I think that's something to ask maybe Jan. And I think Sarah might have looked at some stars like this as well. So in Amsterdam, so they're definitely, yeah, moving into these stars is something that can be done, but maybe there are some issues that you would have to ask them about.
Okay, Sarah is also using Fastwind, right? Or
yeah, so it's essentially the same method. It's Fastwind with a genetic algorithm as well.
okay, I was wondering if there's some physics that you need to be careful with as you push towards that might be missing in Fastwind. Okay, thank you.
Sure, thanks.
Okay, thank you very much, Pablo. So that leaves me with thanking Calum again. Thank you very much for this nice talk, and I'll see everyone the next time.